Can you hear me? Great. Yeah, I'm Lily Puras from DZ Zeuthen, and I will talk about the prospect for cosmic ray measurements with the Radio Neutrino Observatory in Greenland, RNOG. And on top, you see already one of our stations. They're buried in snow, so it's basically solar panels. Yeah. Are we in the right window? Ah, der Weise? Ah, okay, all right. So RNOG is located on the top of the Greenlandic ice sheet on 3.5 kilometer height. And you see here, this is the array we have planned so far. It consists of 35 stations, and those 7 here are the ones we have already built. And each of these dots stands for one of those. And so our station consists of 3 in-ice strings, which are down to 100 meters, and 9 surface antennas here at the top. 3 of the surface antennas are facing upward to detect cosmic rays, and 6 are facing downward, which are also triggering neutrinos. And you see here that they're a little inclined, at least the neutrino ones. This is how we imagine a neutrino event would look like. So we have here a detector, and the neutrino is coming in here, showers, and the radio emission is the strongest on this red cone, which we call maybe Cherenkov cone, because it's a Cherenkov-like effect, which is at 56 degrees in ice. And then our radio emission propagates to our detector. This is our sensitivity prediction, and you see that we not quite get the extended ice cube flux, but we can cut into the area which is allowed from ultra-high cosmic rays. This is for 5 years of RNOG. So now to the possible background events to neutrinos. Ilse already talked yesterday about the neutrinos, and so I will talk more about the surface. I made this little plot where we have here the air-ice interface, and of course we can have cosmic rays and air showers, which then travel to our detector here and can be measured by the surface antennas. What also can happen is that one of the muons out of a cosmic ray travels further into the ice and induce a particle cascade, which pretty much looks like a particle cascade induced by a neutrino. This can happen through catastrophic energy loss. So this is one background we might see. We can also have reflective layers due to difference in the ice densities. And another thing was Simon de Cockere investigated is that vertical cosmic rays have really dense energy cores, so in the center, which can also propagate into the ice and look like in ice induced neutrino induced particle shower in ice. So I'll talk a bit more about the muon background. As we've seen this morning, the muon flux is a tough thing. So I plotted it here for different hadronic interaction models, which is the line style, and for different cosmic ray compositions. So a really proton-rich one and proton-poor one. And you see that at the energies we are interested in, that's like around 10 to the 15 electron volt. This varies about like 3 orders of magnitude. If we follow that together with what RNOG might be able to trigger, then we see that we get maybe 1 muon in 5 years in the full array. This sounds pretty small, but the problem is that's the same order of magnitude we expect neutrinos to occur. And if we have a neutrino event, we really want to make sure it's not a muon. So these huge uncertainties leads us to a mitigation strategy. In this case, we have the advantage that muons stem from an air shower. So the idea is, if we measure the air shower, we can veto the in-ice trigger. So here's a plot showing the numbers of muons per year and the belonging cosmic ray energy. And you see the most muons come actually from really high cosmic rays. And that's good because we're good in detecting high energy cosmic rays. I tried to calculate that a little bit, how good a muon veto would be, and you see that we are pretty good at the lower energies because there's a conventional flux which also stems from high cosmic rays. and we're good at the high energy, but we like a bit of veto efficiency, around 10 to the 15 muon shower energy, muon shower energy in the ice. Of course, this veto efficiency strongly depends on our ability to detect cosmic rays. So I will talk more about the trigger mechanism and the simulations for air showers. This is quite technical. So we have our incoming radio signal, which is here like the simulated electric field. This goes through our antenna and the surface board, which is basically an amplifier. So here we add the detector response and the amplifier. Together, it builds like this trace here in the time and the frequency domain, and you see there's a lot of group delay added because of all the hardware. On this trace, we apply our trigger, and it consists of a filter, a diode, and a coincidence check. If you look here, it's a simple threshold trigger. We use a frequency band which is optimized for the signal so that we reduce noise and get to a lower threshold. And the coincidence check also reduced the trigger rate. The problem is, you see like this air shower signal, it's really like oscillating fast, and that's not good for the FPGA, who has to decide if it's triggered or not. So we need a mechanism to smoothen the signal, and this is done by a diode, in this case a Schottky diode. The Schottky diodes are great because they're super cheap, they consume no power, and they're stable or robust. But the problem is they're quite finicky to model. So because I tried to model it without the hardware, it was quite difficult. So I built a little hardware corner in our office with the with a frequency generator where I fed in like a cosmic ray signal. It went through the trigger board, and then I measured it with the oscilloscope, and this is how it looks like now. It's the smooth curve which the FPGA sees and where the threshold is applied on. The initial trigger design has a really limited sensitivity because we were short in time and hardware, like most experiments are. So here's a cosmic ray simulation. So you probably all know this footprints. A very inclined shower, of course, are able to cover a bigger area of our detector, but also like with 50-degree, we might be lucky to get one. Here are the parameters I used for the trigger, and I used 407 showers, simulated the effective area with 2 different trigger diode response settings, so the smoothing of the trace, basically. What we find out is that the effective area really depends on that trigger shape. So if we use that with the optimistic way, we have a huge or a bigger effective area. And if we use the pessimistic model of the diode, we use a lot of sensitivity below 10 to the 17 electron volt. If you fold that with the OJ flux, which is of course a power law, you see that with the pessimistic scenario, you really miss out on all the cosmic rays below 10 to the 17, which makes the big difference between how many cosmic rays we expect per day. So if we get this lower energy bin, if we are able to measure it, we get like around 80. If we're not measuring it, it's like 8. So that's quite sad, but it also gives us a reason to optimize our trigger. So let me summarize it for you. So RNOG is designed to detect EEV neutrinos, but also detects air shower. The effective area really depends on the trigger characteristic, which are currently under study. The background prediction have large uncertainties, but the goal is that we can use all these background events as a calibration source and to verify that our detector works. The cosmic ray search is in progress, as well as the trigger optimization to increase the numbers of cosmic rays and also obtain a better calibration source. Thank you very much.